So today we talk about relative acceleration analysis. We've spent the last few classes doing relative velocity, and so let's kind of review for just a moment. So we've got a rigid body. We just made this a simple link. So this is going to be undergoing general plane motion, velocity plus rotation. And so if we know the velocity of point A, we can find the velocity at point B by first realizing that the relative velocity B relative to A would be as if B is rotating about point A, and so it would just be omega across the position vector B relative to A. Therefore, the velocity of point B, we just add the translation component, the velocity of A, to the velocity B relative to A, and we have the equation for relative velocity. Now we go through that again just to show that when we look at acceleration, we do a similar kind of thing. Now we could have just omega. We could also have omega changing speed, so we could have an angular acceleration as well. And so point A can have a given velocity. It can have a acceleration as well. And so when we start looking at the acceleration of B relative to A, well, we have a tangential component. In that tangential component, of course, the magnitude is just r times alpha. But to get it as vector form, we use the cross product, just like we did for the velocity analysis. And so the angular acceleration, AB, across the position vector, B relative to A, gives us that tangential component of the relative acceleration. But we know from looking at accelerations of particles on a curved path that there's also a normal component of acceleration back toward the center of curvature, in this case back toward point A. Now we know that the magnitude of that is r omega squared. Now, so in this case we don't need a cross product because the direction is back toward point A. In other words, it's in the negative direction as the position vector r B relative to A. So this simply becomes minus omega squared times the position vector, again with the negative sign just defining the direction of from B toward A instead of the position vector itself. The direction is from A toward B. So don't get that confused. This is not a cross product. Again, this is just a scalar multiplied by a vector. So we add those to the acceleration of point A, and we have our relative acceleration equation with one more term than we have for the relative velocity. So equations get a little bit longer, a little bit messier, but just like with the relative velocity method, it is a step-by-step method. We can work from point to point even for the most complex mechanism. So here's a problem we looked at before from the velocity standpoint. We want to find the angular accelerations, in this case, of BC and CD. Given that we know the angular velocity of AB, we could have an angular acceleration as well, but we'll keep this simple and say we've only got an angular velocity, a constant angular velocity AB, and for a given orientation of theta A. Well, the first step is, just like when finding the velocity, we have to do the position analysis first. We have to know the angles to be able to write the position vectors. Secondly, because of the fact that our acceleration equations involve the angular velocities omegas, we have to do velocity analysis next. So we have to do the position and velocity analysis before we're even ready to start with the acceleration analysis. But now, because I know that the A is a fixed point, I know what omega is. In this case, we said omega is constant. So in addition to saying the acceleration of point A is 0, we can also say that the angular acceleration of AB is equal to 0. And so we come up with the acceleration of point B. Once we know the acceleration of point B, we work from B to C. And so there's our first equation, again just plugging in that acceleration of C relative to acceleration of B. But again, I've got too many unknowns to solve. So just like with the velocity analysis, I realize that point C is not only on link BC, it's also on link CD. So I can write an equation for the acceleration of C relative to acceleration of D, which of course is equal to 0. So now setting those two equal to each other, I can now solve for my two unknowns, which are alpha BC and alpha CD. There's a lot of steps to this, but again, it's a systematic approach that can be used for the most complex mechanism. But as we said, it is lengthy, and when you get done, all I have is what are the acceleration values for that specific angle of AB that I picked. And so sometimes you'll want to know, well, when is that the maximum value? And so you have to work through it again or set it up on a spreadsheet. And so for that reason, you find that motion analysis software is really helpful for that, because then you can run the analysis for a full range of motion and find out where the maximum acceleration occurs. So that's it for the kinematics of rigid bodies. Next time we'll start on kinetics. So with particles, remember our basic equation was that we sum forces to get the mass times acceleration. Well, that works if you only have translation. So with a rigid body, you can have rotation as well. And so in addition to the sum of the forces equation, we'll have a sum of the moment equation that involves angular acceleration and a quantity that we'll learn to calculate called the mass moment of inertia.